Welcome to the deep dive. We're here to take really dense scientific thinking and, well, make it make
Make
sense.
it digestible.
Exactly. And today we're diving into maybe the biggest question there is. How did the universe actually begin? Specifically, that first tiny fraction of a second and the whole idea of cosmic inflation.
Right, this incredibly rapid expansion right after the Big Bang.
Mm.
It's the standard picture, the one most physicists work with.
But we're going to be looking at some sources today that suggest maybe that standard picture has some issues, some cracks in the foundation, you could say.
Definitely. It's been the dominant theory for decades, explaining how the universe just ballooned outwards at this, well, frankly, ridiculous speed. Exponential growth.
So our mission today, it's kind of threefold. First, let's really get clear on what standard inflation theory is, and crucially, what big problems it actually solved. Because it did solve some major puzzles.
It wasn't proposed just for fun. It fixed things the original Big Bang model couldn't.
Second, we need to look at let's call it the messy part, the sort of fixes that were needed, specifically this hypothetical thing called the inflaton field.
Ah, yes, the inflaton, the sort of magic ingredient cooked up to make inflation work.
And third, this is the exciting part, we'll unpack a newer idea, a really different take that tries to ditch all that exotic stuff and just use gravity, plain old gravity, basically.
A much simpler, more elegant approach, potentially, relying on vacuum energy, space-time itself.
Now, before we jump in, we really need to stress how incredibly hard this field is. I mean, you're trying to piece together what happened 13.8 billion years ago.
Yeah, from basically just echoes and faint signals, like the cosmic microwave background, the CMB, the amount of actual data is tiny.
It's not like the original scientists weren't smart. It's the ultimate cold case. Almost no clues left behind.
Exactly. And the solution we settled on, inflation, it feels a bit contrived sometimes. You have to invent this temporary energy source.
But the problems it solved were so fundamental that, well, we've stuck with it.
Right. But keeping it means wrestling with some tricky questions about, what makes good science?
Yeah.
Is it too flexible? Can you make it fit anything? That's what makes this alternative so interesting to look at.
Okay, let's dig into that standard model first, the consensus view. What's the core idea of inflation?
The core idea is that for a vanishingly small moment right after the Big Bang, the universe underwent this period of exponential expansion, faster than light even.
Exponential. What does that really mean here? Not just fast, but acceleratingly fast.
Yeah, think compounding interest, but for space itself. It wasn't just stretching linearly. The rate of stretching was itself increasing incredibly rapidly. We're talking about the period between maybe 10 to the minus 36 and 10 to the minus 32 seconds after the bang.
I can't even picture that time frame.
Nobody can, really.
Yeah.
But in that instant, the universe is thought to have expanded by a factor of at least 10 to the 26. That's a 1 with 26 zeros after it.
Okay, so something the size of a proton becomes astronomically huge.
Pretty much, yeah. The entire observable universe today was compressed into something smaller than an atom, and then bam, it inflated to maybe the size of a grapefruit almost instantly.
You said faster than light expansion. How does that work with Einstein? I thought nothing goes faster than light.
Ah, good point. That's a common confusion. Nothing can travel through space faster than light. But this wasn't about movement through space.
It was space itself.
Exactly. The fabric of space-time itself was expanding. General relativity limits speed within space-time, but it doesn't actually put a speed limit on the expansion of space-time. It's a subtle but crucial distinction.
Okay, got it. So this wild idea became the standard because it solved problems. You mentioned three big ones accidentally.
Well, accidentally might be strong, but it turned out to be incredibly effective at solving problems it wasn't initially designed for. The biggest one is the CMB uniformity, the horizon problem.
Right, the cosmic microwave background, that afterglow from the early universe. If you, the listener, look at maps of the CMB, it's incredibly smooth.
Astonishingly smooth. The temperature is about 2.7 Kelvin, give or take, everywhere we look. The variations are tiny, like 1 part in 100,000.
So why is that smoothness a problem for the original Big Bang theory without inflation?
It's about communication
Oh,
or causal contact. In the old model, without that super rapid expansion phase, if you look at 2 points on opposite sides of the sky in the CMB, they are so far apart that light or any information simply wouldn't have had enough time since the beginning of the universe to travel between them. They were never in causal contact.
So they couldn't have talked to each other to agree on a temperature.
Yeah.
Like two strangers on opposite sides of Earth having the exact same body temperature without ever meeting. It shouldn't happen.
Precisely. How do they coordinate to reach the same thermal equilibrium if they were never connected?
And inflation solves this how? By starting smaller.
Exactly. Inflation says, hold on, before that massive expansion, the region that would become our entire observable universe was incredibly tiny, microscopically small.
Ah, so it was small enough to actually interact.
Yes, it was causally connected. It had plenty of time to smooth itself out, reach a uniform temperature, just like stirring a cup of coffee. Everything mixed together.
Then inflation hits.
And it takes that tiny uniform patch and stretches it exponentially, blowing it up to cosmic size. The uniformity gets locked in and spread across the whole sky. Horizon problem solved.
Okay, that's elegant in a way. Triumph number one. What's number two?
Number 2 is structure seeding. We said the CMB is almost perfectly smooth, but not quite. It had those tiny fluctuations, those
Oh, with 1 part in 100,000 variations.
right, and those tiny variations are absolutely crucial. They're the seeds for everything we see today: galaxies, galaxy clusters, the whole cosmic web.
Because gravity acts on them, denser spots pull in more stuff.
Exactly. Slightly denser regions had slightly more gravity, started pulling in matter, and over billions of years grew into the structures we observe. Without those initial seeds, the universe would just be a uniform, boring soup of gas.
So where did the seeds come from in the standard inflation story?
From quantum mechanics. Inflation theory proposes that even in the supposedly empty vacuum of the very early universe, there were constant quantum fluctuations, tiny, unpredictable jitters in energy and fields.
The quantum foam sort of thing?
Kinda, yeah.
Yeah.
The idea is that inflation took these microscopic, subatomic quantum jitters and stretched them massively.
Blew them up to astronomical scales.
You got it. Stretched them into the macroscopic density variations that we see imprinted on the CMB. So, inflation provides a mechanism, albeit an indirect one, for creating the initial lumps and bumps needed to build the cosmos.
Okay, so it explains the overall smoothness and the tiny ripples needed for structure. That's pretty powerful.
Very powerful. It ties large-scale structure back to quantum physics in the first instant.
But you mentioned irony earlier. These huge successes weren't the original point.
Correct. It's quite ironic. The theory, first proposed seriously by Alan Guth and others around the early 80s, was primarily aimed at solving the monopole problem.
Magnetic monopoles, like a North Pole without a South Pole.
Exactly. Some very popular theories back then, called grand unified theories, or GUTs, predicted that just after the Big Bang, the universe should have been absolutely flooded with these hypothetical particles, magnetic monopoles.
But we've never found one, right? Despite looking really hard.
Never. Not a single one. And if they existed in the numbers predicted by GUTs, their mass would dominate the universe. It would look totally different.
So inflation was invented to get rid of them.
Essentially, yes. Inflation solves the monopole problem by saying the exponential expansion diluted them incredibly effectively. It spread them out so vastly that the chance of finding one in our observable patch of the universe today is practically zero.
They're just too far apart now.
Right. But here's the deep irony our sources highlight. What if magnetic monopoles just don't exist? What if those GUTs were wrong?
Ah, then inflation was invented to solve a problem that wasn't actually a problem.
Precisely. It's possible the whole elaborate mechanism was built on a false premise. Yet we can't just throw it away because it works so beautifully for the horizon and structure problems.
So we're kind of stuck with it, even if its original motivation might be moot.
That's the situation. It's a theory proposed perhaps for the wrong reason, but which turned out to be spectacularly good at fixing other very real cosmological headaches.
But it's not perfect. You mentioned two big gaps, even with its successes, the trigger and the end.
Yes, the trigger problem and the end problem. What force, what mechanism actually kicked off this period of hyperexpansion? And maybe even more critically, what turned it off? Why did it stop so abruptly, and how did all that energy driving the expansion get converted into the normal matter and radiation of the hot Big Bang?
It couldn't just keep inflating forever.
Right, it had to stop and reheat the universe, creating the stuff we're made of. Solving these trigger and end problems is where things get, well, complicated, and where that flawed patch comes in.
Right, the creative accounting you mentioned. To plug those gaps, the start and the stop, physicists basically had to invent something. This is the inflaton field.
Yeah, the inflaton is a classic example of what we call an ad hoc solution in physics.
Oh.
It wasn't discovered. It was proposed specifically to make inflation work.
So what is it supposed to be? Some kind of energy field.
It's hypothesized to be a scalar field. Think of it like the Higgs field, something that permeates all of space and has a value or energy potential at every point. But unlike the Higgs, Its properties are completely tailor-made for this one job,
Hmm.
driving inflation and then stopping.
Tailor-made how? What does it actually have to do? Sounds like it has a lot on its plate.
It had three incredibly demanding jobs, really. Job one,
Hmm.
drive the rapid expansion. It needs to have this huge potential energy that dominates the universe right at the start.
Okay.
And this energy has to create something called negative pressure. That's the key.
Negative pressure. That sounds weird. Normal
What?
pressure, like in a tire, pushes outwards, right? Positive pressure. What does negative pressure do?
It's a concept from general relativity. Gravity responds not just to mass and energy density, but also to pressure. Normally, positive pressure adds to gravity, helping to slow down expansion. But if you have a field, like the inflaton is supposed to be, with a large potential energy and very little kinetic energy, its pressure becomes strongly negative.
And negative pressure causes anti-gravity.
Effectively, yes. It acts repulsively. This huge negative pressure generated by the inflaton field's potential energy is what pushes space-time apart, driving that exponential expansion. It's the engine.
Okay, engine check. Job two, it had to make the seeds for galaxies, right?
Right. Job two, generate the quantum fluctuations. The theory says the inflaton field itself, being a quantum field, isn't perfectly smooth. It has its own tiny quantum jitters.
Like the vacuum fluctuations we talked about earlier.
Exactly. And as the inflaton field is slowly rolling, changing its value during inflation, what we call the slow roll phase, these quantum jitters in the field get stretched by the expanding space.
So the field's own wobbles get amplified.
Amplified and frozen into the fabric of spacetime as density variations. Those become the seeds for structure. So the inflaton both drives the expansion and creates the necessary lumpiness.
Okay, that's clever. Job three, it has to stop.
Job three, decay into ordinary matter. Inflation has to end. The inflaton field needs to somehow convert all its potential energy into the particles and radiation electrons, quarks, photons that filled the hot early universe.
How does it do that? Does it just run out of steam?
The idea is that the field's potential energy is like a ball sitting on a high, very flat plateau. That's the slow roll phase driving expansion. But eventually it rolls off the edge of the plateau and falls into a deep valley.
Ah, phase transition.
Kind of. As it oscillates back and forth at the bottom of this potential energy valley, it violently dumps its energy, creating a shower of particles. This is called reheating. It populates the universe.
Wow. Okay, so drive, expansion, create seeds, then decay and reheat. That sounds like an incredibly fine-tuned process. That plateau has to be just the right flatness, the cliff, just the right steepness.
Exactly. And that's the core problem. The required shape of this potential energy landscape for the inflaton is extremely specific. It needs to be flat enough for inflation to last long enough to solve the horizon problem, but then steep enough to end quickly and reheat efficiently.
And since we haven't actually seen this inflaton field,
We're basically free to invent whatever shape of potential energy curve we need to match the observations. We design the field to give us the universe we see.
that sounds problematic, like writing the exam questions after you already know the answers.
It leads directly to what's called the overfitting problem. This is maybe the most serious scientific criticism of standard inflation.
Overfitting, meaning you can make it fit anything.
Pretty much.
Mm.
Because if you look at the scientific literature, there isn't just one model of inflation, one specific shape for the inflaton potential. There are literally hundreds of different inflation models.
Hundreds, really?
Yes, it's a huge number. People have proposed polynomial potentials, exponential potentials, hybrid models, brain inflation models, all sorts. Every time new data comes in from the CMB, if it doesn't quite fit the simplest models, theorists can tweak the potential or invent a new one to match it.
And each model probably has its own settings, its own knobs to fiddle with.
Exactly. Each of these hundreds of models comes with multiple free parameters. These are numbers in the equations controlling the flatness of the plateau, the depth of the valley, the coupling strengths for reheating that aren't predicted by the theory itself. You just adjust them, you tune them, until the model's output matches the CMB data we observe.
So if you have hundreds of models and each model has, say, 5 or 10 adjustable knobs,
You can basically fit any reasonably smooth data set. It becomes almost impossible to falsify the general idea of inflation because if one specific model fails, you just say, okay, that potential shape was wrong, let's try this other one with slightly different parameters.
that feels less like prediction and more like post-diction, explaining after the fact.
That's the criticism. A truly powerful scientific theory should make specific, risky predictions before the data comes in. If a theory is so flexible it can be adjusted to fit anything, it loses that predictive power. It becomes more of a descriptive framework than a fundamental law.
Is that why, despite solving these huge problems, there hasn't been a Nobel Prize for inflation?
That's very likely a big part of it. Our sources strongly suggest this. The lack of a single, unique, agreed-upon mechanism, the reliance on this invented inflaton field with all its adjustable parameters, it makes the whole framework feel a bit slippery, scientifically unsatisfying to many.
Okay, so inflation works incredibly well descriptively, but the underlying mechanism, the inflaton, feels like a patch-up job with too many adjustable parts.
That's a good summary. Necessary, perhaps, but philosophically messy. Which brings us to the alternative idea.
Right, the search for something cleaner, simpler, getting rid of the inflaton altogether.
Exactly. The core idea behind this new approach is minimalism. Can we explain that early burst of expansion using only the ingredients we already know exist, primarily gravity itself, as described by general relativity?
So the absolute key difference, no inflaton field, just gravity and maybe vacuum energy.
Precisely. It uses the concept of the cosmological constant, but in a very different way than we think about it today.
Okay, the cosmological constant. Today, we usually associate that with dark energy, right? This tiny amount of energy in empty space that's causing the universe's current, very slow acceleration.
Correct. It's incredibly small today. But the trigger in this alternative model is the hypothesis that the universe began with a huge, positive cosmological constant.
So the vacuum energy density was enormous right at the start.
Orders and orders of magnitude larger than it is now. And remember what a large positive energy density implies in relativity.
It creates negative pressure, like the inflaton was supposed to.
Exactly. A large cosmological constant inherently produces enormous negative pressure. So right from the start, the vacuum energy itself acts as the engine for inflation.
So you don't need a separate field rolling down a hill. The energy of empty space itself provides the anti-gravity push.
Precisely. The expansion happens naturally just due to the initial high-energy state of the vacuum. The start problem is solved using a known component of Einstein's equations, just dialed up to 11.
Okay, that sounds much simpler for starting inflation, but the stopping problem was always the hard part for the inflaton. How does this gravity-only model stop the runaway expansion?
This is where it gets really neat, I think. The model suggests that a universe undergoing such rapid expansion, driven solely by a massive cosmological constant, is fundamentally unstable.
Unstable. How so? It sounds pretty uniform and smooth if it's just vacuum energy.
It's uniform, but it's under incredible gravitational stress, you could say. And the key is, again, quantum fluctuations, but not fluctuations of an inflaton field.
Fluctuations of...
Fluctuations in space-time itself. The gravitational field, the vacuum, is always subject to quantum jitters. In this incredibly high-energy, rapidly expanding, unstable state, these tiny quantum fluctuations in space-time don't just get smoothed out. They start to grow.
Grow. How does that stop inflation?
As these space-time fluctuations grow, they create inhomogeneities. They start to introduce structure and complexity into the gravitational field itself. Think of it like ripples building up on a perfectly smooth, rapidly stretching sheet.
Okay.
Eventually, these growing fluctuations reach a critical point where they gravitationally disrupt the smooth exponential expansion.
Yeah.
The increasing gravitational lumpiness generated by the amplified vacuum fluctuations essentially breaks the spell.
So the expansion kind of trips over its own quantum feet. The instability causes it to collapse.
That's a good way to put it. The system undergoes a kind of phase transition, driven by its own internal quantum gravitational dynamics. It can no longer sustain that simple, uniform, exponential expansion, and it naturally, abruptly transitions into the hot, dense, radiation-dominated state of the standard Big Bang.
Wow. So it stops itself. No need for a field to conveniently fall off a cliff.
Exactly. The end problem is solved intrinsically by the instability of the inflationary state itself.
And what happens to the huge cosmological constant after this transition? It has to become the tiny value we see today.
The model suggests that during this transition, as the universe settles down into the hot Big Bang phase, the effective value of the cosmological constant also drops dramatically, leaving just the small residual constant that drives today's gentle acceleration. The transition mechanism naturally resets it to a low value.
Okay, that covers the start and the stop without an inflaton. What about the seeds for galaxies? The inflaton made those from its own quantum jitters.
In this model, they come from the very same fluctuations in space-time itself that caused inflation to end.
The ones that grew and disrupted the expansion.
Yes. Those quantum gravitational fluctuations, amplified and stretched during the rapid expansion phase, are precisely the primordial density perturbations needed to seed structure formation. They get imprinted onto the matter and radiation that emerge after the transition.
So gravity and its quantum nature do everything. Drive the expansion, stop it, and create the seeds.
That's the beauty of it, according to the proponents. One mechanism, rooted in known physics, general relativity, and quantum fluctuations, handles all three jobs. No extra fields required.
Okay, putting these two side by side, the gravity-only model definitely wins on elegance, right? No made-up fields, just gravity doing its thing in an extreme environment.
Philosophically, it's much more appealing, yes. It adheres to Occam's razor, don't multiply entities beyond necessity. If gravity can do the job, why invent something new?
The simplicity is striking. Gravity explains the start and end. No exotic fields needed.
And scientifically, the most compelling argument is the parameter count. This really gets to the heart of the difference in predictive power.
Right. We said standard inflation has hundreds of models, each with multiple knobs to tune the free parameters.
Dozens, maybe hundreds of parameters across the whole landscape of inflation models. You adjust the shape of the potential, the initial conditions, the reheating couplings. Lots of freedom to fit the data, which leads to that overfitting concern.
So how many parameters does the gravity-only model have?
Just one.
One! Seriously.
One primary free parameter. That parameter basically sets the energy scale or the initial expansion rate during that early phase driven by the large cosmological constant.
And what does that one parameter predict?
You can directly link that single parameter to the overall amplitude of the density fluctuations we see in the cosmic microwave background, how strong those initial seeds were.
So you measure the strength of the CMB ripples, and that fixes the only free parameter in the theory.
Essentially, yes. It makes the theory incredibly constrained and highly testable. If future, more precise measurements of the CMB fluctuation amplitude shifted even slightly, this simple model could be ruled out immediately.
That sounds like much stronger science. Falsifiable.
Absolutely. A one-parameter theory that explains multiple phenomena is vastly more powerful than a multi-parameter framework that can be continuously adjusted.
And does this one parameter model actually match the key CMB features, the uniformity, the seeds?
According to the papers we looked at, yes. It naturally explains the near scale invariance of the perturbations.
Scale invariance, meaning the ripples had roughly the same strength on all different size scales, which is what we observe and need for structure formation.
Correct. The model produces that feature without special tuning. It also seems to account for the absence of certain correlations between different modes in the CMB data that some of the more complex inflation models actually predict, but which haven't been clearly observed. It fits the simplicity of the data quite well.
Okay, so it's minimal, uses known physics, has only one parameter, and matches several key observations. It sounds amazing. Why hasn't it taken over? What's the catch?
The catch. There is a significant one, a critical caveat. There's one specific, quite subtle, observational prediction that standard inflation did make successfully, and which this gravity-only model, at least in its current simplest form, fails to address.
Okay, what is it?
It's the correlation between temperature and polarization in the CMB.
Temperature and polarization, right? The CMB isn't just temperature, it's light, and light can be polarized.
Exactly. The light from the CMB scattered off electrons in the early universe, and that scattering process polarized the light, meaning its electromagnetic waves tend to vibrate in preferred directions. We can measure this polarization, often described using patterns called E modes and B modes.
Okay.
Now, standard inflation, the versions involving a slowly rolling scalar field, naturally predicts a specific relationship, a specific correlation between the hot and cold spots, temperature anisotropies, and the E-mode polarization pattern.
Why does it predict that specific correlation?
It comes down to the way inflation generates the perturbations. It produces not only density fluctuations, scalar perturbations, but also faint ripples in space-time itself, primordial gravitational waves, tensor perturbations.
Oh, okay.
These gravitational waves subtly stretch and squeeze space-time as they propagate, and this affects how the CMB light scatters off the plasma just before it's released. This leaves a characteristic imprint in the way the temperature variations correlate with the E-mode polarization. It's often called the TE cross-correlation spectrum.
And that specific TE correlation predicted by standard inflation
Has been measured and confirmed by experiments like the Planck satellite. It's considered one of the key predictive successes of the standard inflationary paradigm.
and the gravity-only model.
In its current formulation, it doesn't naturally produce this specific type of TE correlation signal, or at least not in the way that matches the observations precisely. It handles the density fluctuations well, but seems to miss this subtle polarization effect linked to primordial gravitational waves generated during standard inflation.
So that's the sticking point. The elegant new theory fails one crucial test that the messy old theory passed.
That's the crux of it. It's a major hurdle. Elegance and simplicity are wonderful, but ultimately, theories live or die by their agreement with observation.
How did the source material rate this new model overall then?
It gave it a solid 8 out of 10. High praise for the ambition, the parsimony, the elimination of the inflaton, but it specifically docked points for not yet explaining that observed temperature polarization correlation.
So, beautiful theory explains a lot with just one parameter, but it's missing that one piece of confirmed evidence that its competitor has.
Exactly. It's a compelling contender, but it hasn't delivered the knockout blow because of this specific observational gap.
Stepping back from the specific models, this whole debate, inflaton versus pure gravity, really highlights something fundamental about doing cosmology.
Absolutely. It underscores the incredible difficulty of the task. It's not that physicists aren't clever enough. It's about the profound scarcity of data.
We're trying to reconstruct the first tiny fraction of a second, 13.8 billion years ago, based on
Right.
the CMB light released 380,000 years later, and maybe some element abundances.
Pretty much. It's like trying to understand the intimate details of an engine's ignition sequence by looking at a blurry photo of the exhaust fumes from miles away billions of years later.
Right. Every tiny detail in that CMB map, the exact pattern of hot and cold spots, the polarization angles, becomes this incredibly precious clue that theories have to explain.
And maybe if we had more direct probes, more fossils from that earliest moment, the picture would be clearer. Perhaps the need for hundreds of tunable inflation models wouldn't have arisen if the data was more constraining from the start.
It makes you appreciate just how amazing it is that we can build models that work at all.
It really is. The fact that we have any models, whether it's the standard inflation model predicting TE correlations, or this new gravity model explaining scale invariance with one parameter that can make testable predictions about the universe's origin based on such limited evidence is, frankly, astounding.
It shows the power of theoretical physics and mathematical modeling.
And it also shows the scientific process in action. This tension between a potentially messy but observationally successful theory and a beautifully simple but incomplete alternative, that's what drives progress. Pushing for elegance forces us to question assumptions, like the necessity of the inflaton.
Yeah, the willingness to challenge even a deeply entrenched idea like inflation, demanding simpler explanations if possible, that feels like science working as it should, even if the final answer isn't clear yet.
Exactly. It's about intellectual honesty and constantly testing our foundations. Hashtag tag tag outro.
Okay, so let's try to boil this deep dive down. What's the core takeaway?
I think the central story is this potential shift away from complexity towards simplicity. We started with standard inflation theory, essential for explaining the universe's smoothness and structure, but relying on this invented inflaton field.
A field which leads to this overfitting problem, with hundreds of models and tons of adjustable parameters, making it hard to truly test.
Then we explored this compelling gravity-only alternative. No inflaton needed. Instead, a huge initial cosmological constant drives the expansion, which then stops naturally due to inherent quantum instability.
And the big selling point there is its incredible simplicity. Just one free parameter needed to match the basic CMB observations.
But the major hurdle, the reason it's not yet the new standard, is that it currently fails to predict the specific temperature polarization correlation seen in the CMB, a key success of the standard model.
Right. That TE correlation is the elephant in the room for the gravity-only model.
It is.
Yeah.
Which leads us to the final thought, something for you, the listener, to mull over.
Okay, leave us with something provocative.
Well, that TE correlation signal hinges on primordial gravitational waves generated during standard inflation being strong enough to detectably influence the CMB polarization. Now imagine two possibilities. What if future, even more precise CMB observations show that correlation isn't quite what simple inflation predicts? Maybe it's weaker or different. Or what if theorists find a clever way for the gravity-only model, perhaps with some refinement, to naturally produce the observed TE signal using just space-time fluctuations without needing an inflaton?
Okay.
If either of those happened, how radically would it change things? Could we potentially discard the entire complex edifice of inflaton physics built up over decades and explain the universe's fiery birth using essentially just Einstein's gravity and quantum mechanics.
Reducing the origin story to its absolute bare essentials, gravity as the sole architect.
It's a tantalizing prospect, the ultimate simplification. But whether the universe is actually that simple, well, that's what future observations will hopefully tell us.
A fantastic cliffhanger. Thanks for exploring that with us, and thank you for joining us for the deep dive.